Our next presenter is Boris Greenberg.
Yep.
Boris is VP of XR Solutions VoxelSensors. Boris has 21 years of experience in multidisciplinary R&D teams and more than 20 patents. So please welcome Boris.
Hello, everyone. So what we do in VoxelSensors is essentially developing a new technology for 3D sensing and eye tracking. I'm going to talk mostly about the 3D sensing in this talk. So one thing that is a problem in the current situation is the fact that even the state-of-the-art technologies are not getting adopted widely in the world. And the reason for that is that it's super power hungry and it has a lot of limitations. Now, this spatial computing is essentially the next big thing in computing revolution. And also what is required is to have a device that is sleek enough, small enough, low power and accurate enough for the users to feel or to use it all day long, and for it to be useful, helpful, and to be connected all the time. So this contextual sensing or 3D sensing in general, it's something that is a long-standing problem, and it has many aspects that is included in that. One is SLAM and general odometry, essentially everything that is used for 3D mapping of the world. The other is segmentation and the object identification, actually understanding what it is that we have in the world. The other is tracking the user, meaning tracking the hand and the hands, the manipulation, interaction, and also to track the user in a sense of gaze. And other aspects is segmentation and indexing of the environment, because we need to understand the context of what is going on, and also some biometric tracking of the user himself or herself. So we can actually separate this task or this problem into various sub tasks, such as, for example, power efficiency, and that can be described in battery life, but also with a lightweight device. So essentially, if you have a brick with you, it's not something that you're going to use all day long. The other part is latency. So you want the tracking of the objects in the world to be very fast, so you will not see any discrepancy between the motion of the real world and what you're actually projecting to the user. Then you want a very high accuracy. So this is very important, because you want the experience not to break. Essentially, you want to embed the virtual objects, so to create the right dynamics of the objects themselves. And then it needs to be robust and durable in the sense that it should work in any kind of environment, basically resistant to any kind of ambient situation, and also concurrent devices, and also operation in various light modes. So the main thing about this that there is a tension in this space. The problem is that the tension is between performance and power consumption, and also between latency and accuracy. So the solution is to change the our solution is to change the sensing paradigm. Essentially, not to add more sensors, but to build a different kind of sensor, and also to evolve computer architecture. I'll talk more about that. And that will manifest itself in efficient active event sensors. That's the core of our technology, and also the progressive compute pipeline. So our approach to that is these two aspects. So we have a low power, low latency sensor, and I'll explain more what it means. And then on the other side, reduce the power, we have also low power, low latency in progressive scanning. So essentially, what you can see here, is it possible to see? Oh. Here. You can see here, we have a laser source that is creating a laser pattern, and then you have a sensor that picks this pattern up, and we recreate this pattern in the sequential, basically event-based method. But that event-based method is actually built in such a way that that you can see on the left here the pattern that is being projected to the world, and then the sensor that has what is called SPAD, single photon detector, and then a layer of logic that is kind of building a kernel in temporal and spatial correlation in such a way that that you are able to detect only the pixels that are relevant to this beam that is projected. And this one signal, one source, so basically one laser source, vector to the world, and the vector from the world to the sensor is what recreates the 3D structure from two XYT coordinates. So what it means is that by projecting, you can create a 3D image on the fly. And this 3D image is a representation with 1 order of magnitude less power consumption than competing technologies such as time of flight or structured light. And also it is able to do that at the sample rate of 100 megahertz, which is significantly faster than anything that is being able to do it in competitive, because it's not a frame-based, it's asynchronous. So it means that, for example, objects like a fan can be detected without any smear, because the sampling rate of any pixel is 10 nanoseconds. Not only that, what you can create is essentially time of flight. So what you see on the left is what is being done in the world. On the right is what happens in the system, in our system, and in the center is what is happening in the frame-based system. So in comparison to other systems where you need to wait for a frame, here you can create segmentation and indexing on the fly. And that essentially is what brings to the next phase, and this is skipping the point cloud. Essentially, because we are able to use the nature of the scanning light, we can create parametric curves, and these parametric curves can bring can start the process of tessellation much faster, and basically assist us with creating the mesh of the world, or understanding of the world in terms of curvature of surfaces and their relative position in real time. So yeah, thank you.